All right, we're recording. So last time we defined the exponential generating function, and I've actually got, that was one of the last pages we had, something like that. So some of that, I think, some of example 336 we kind of did by, just me fiddling around, but we'll go through it anyway. So I'm on top of page 30 in the notes, example 336. So we're going to find the exponential generating function for this sequence, and I know we've done this one. So that's going to correspond to the sum as k goes from 0 to infinity of x to the k over k factorial, each of those times 1, and that is, of course, e to the x. So here, this next one, B, we've got the number of k permutations of an n set. That's P of n comma k. We can write that as n to the k falling. Or just n factorial over n minus k factorial. Any way like that works. So that's going to correspond to the sum. This is the notation that I'm going to use here inside my sum. The sum as k goes from 0 to infinity of n factorial over n minus k factorial times x to the k over k factorial. This is the sum as k goes from 0 to infinity of n choose k, x to the k, which is 1 plus x to the n. How about C is the sequence 3 to the k? So then this is going to correspond to the sum as k goes from 0 to infinity of 3 to the k times x to the k over k factorial. That's going to be equal to the sum as k goes from 0 to infinity of 3x to the k over k factorial. And just pointing out that when you get this, I think I'm supposed to put a new homework assignment out there probably today. But when you get questions like this in the homework assignment, we ask you to write the generating function. We do not want you to stop here. We want you to do whatever you can to get it simplified, to get it into a closed form if possible. And if it's not possible to get it into a closed form, to at least get it into something like the simplest sum form you can. So this would be e to the 3x. And let's see, that was C. So D is 2, then 1, 2, then 1, 2, then 1. I'm going to rewrite this as 1, 0, 1, 0, 1, 0, plus 1, 1, 1. And then say that corresponds, this second guy is easy. That's just e to the x, right? We just did that up there. But this first guy here, we only get even k. So this is the sum as k goes from 0 to infinity of e to the 2k over 2k factorial. Not e to the 2k, x to the 2k over 2k factorial. This one here we can write as, that is the hyperbolic cosine of x plus e to the x. So probably you guys don't remember those as well from Calc 2 or wherever, but essentially the hyperbolic functions have power series exactly like the trig function of the similar name, except without the -1 to the k. So hyperbolic cosine is x to the 2k over 2k factorial summed. There are other ways that we can write this one. We could have written it as 2e to the x minus, double check, make sure that works. I have a 2 everywhere. Minus hyperbolic sine x. There are a handful of ways to write that. If I had treated this instead as the sequence of all 2's minus the sequence with 1's in the odd positions, then I would have gotten this guy. All right, and then e is just 0, 1, 1, 1, and so on. And so how do we handle a shift here is essentially the question. This corresponds to the sum as k goes from 1 to infinity of x, too high, sorry about that, x to the k over k factorial. But this is equal to the sum as k goes from 0 to infinity of x to the k over k factorial. And then all I've got to do is figure out what I added in to get that sum, and that's just 1, right? When k is 0, that'll be 1 over 1. So I just need to subtract 1. So this is e to the x minus 1. All right. Example 337, we start with the exponential generating function, and we want to find the sequence. So 4 plus 4x plus 4x squared plus 4x cubed. That equals 4 times the sum of x to the k as k goes from 0 to infinity. And then in order to figure out what this sequence is, I need to write it in exponential generating function form. So this is, I'm actually going to put the 4 on the inside so we don't lose it. 4 times k factorial times x to the k over k factorial. So here my sequence hk is 4k factorial. A lot of students, when they're doing these, get it mixed up. They know they need a k factorial in the denominator, and they divide the 4 by k factorial. But remember, we had to write the generating function out and then multiply and divide. And this part stays, that's the kernel of the generating function. And this is our sequence. How about x squared plus 5e to the x? Well, this is equal to x squared plus the sum of 5x to the k over k factorial as k goes from 0 to infinity. So this one is a sequence of all 5's, and this one needs to have a 2 factorial in the denominator, so it'll have a 2 factorial out front. So this is the sequence 0, 0, 2, 0, 0, 0, and so on, plus the sequence of all 5's. So we can just write that as 5, 5, 7, 5, 5, 5, and so on. And in this case, there's not a nice formula way to write it out because there's not a nice formulaic way to say only bump that one by 2. All right. I'm actually going to do example 339 before theorem 338. So if you have a bag containing one yellow ball, three red balls, let me do it that way, and five green balls, how many arrangements of K balls are possible? So if K is 1, this is easy. There are, now the yellow, red, and green are indistinguishable within a bag. So there are exactly 3 arrangements of one ball. What about 2 balls? Here it gets a little tricky. It actually depends on whether you pick a yellow ball or not, right? If you pick a yellow ball first, then there are 2 other balls you can pick. So that would be 2. Plus, if you don't pick a yellow ball, that gives you 2 options for your first ball and 3 options for your second. Double check and make sure that makes sense. This is not how I normally do this question. I just thought it'd be nice to kind of enumerate the first couple of cases, but that gives me more than if I had, no, it doesn't. If I had multiple yellow balls, then I'd have 9 possibilities, right? Can I say it again? Yeah. So if, I'm going to say it 2 ways. So I have 2 possibilities here because there's only one yellow ball. If I pick that first, I can't pick another yellow ball. So if I pick the yellow ball, that's this case, then I have 2 choices. It's 1 way to pick a yellow ball, and then 2 ways to pick between red and green for the second ball. If I don't pick a yellow ball, then I have 2 choices for my first ball, red or green, and then 3 choices for my second ball because I can pick from any of the bags because I haven't depleted them all. That's one way to look at it. The other way is to say, well, if there were no limit on these, then it would be 3 squared ways, but I'm limited in that I can only pick the yellow ball once. So I lose the YY choice from the 3 squared. And so that would be 9 minus 1. In both ways, I get 8. K equals 3. This is going to work really similarly to this case. As a matter of fact, it's probably the easiest way to think about it is if I had an unlimited supply of balls, then I could pick 27 different combinations, 3 to the third, but I lose all of the ones that have 2 or 3 yellows in them, which is 3 choose 2 and 3 choose 3. 3 choose 2 is 3, and 3 choose 3 is, of course, 1. So I get 27 minus 4, which is 23 ways. Now, I think we can do that the other way, too. We can say, well, if I pick a yellow for the first one, there's only one way to do that. And then I have two choices for the second and 2 choices for the third. If I don't pick a yellow on the first choice, then I have 2 choices. But now if I pick a yellow on the second choice, then I only have 2 choices for the third. If I don't pick a yellow on the second choice, then I have, so this is didn't pick a yellow on the first or the second, so I'll have 3 choices on the third. And let's see if that comes out to be the same. I hope it does, because that's pretty sure that's right. So that's 2 times 2 plus 2 times 6. So that's, ooh, I'm off by something. So that's 8 times, that's 20, right? Let's see. I'm going to guess that I made a mistake assuming that was the only ways to get 2 or 3 yellows, although I don't think so. Let's see. Maybe I have skipped something here. Oh, no, I did. I think. No, that includes you choose a yellow on the first, the second, or the third. I'm actually not positive. You think the second? I think the second way is correct too. I think it's much more likely I forgot to subtract something than it is that I forgot to add something. Well, let's figure it out another way. Let's see. Hang on, I'm looking in my supplementary notes here. I'm trying to remember what I thought I had this example written down. Already worked out. All right, we'll have to just work through it. So we have a bag containing 1 yellow ball and then 3 red balls and 5 green balls. And so the number of ways to draw a yellow ball accounting for, okay, hang on. 6 ways to have 2 yellows. Okay, yeah, I was thinking, well, of the 3 positions, if 2 of them are yellow, then that's 3 choose 2 number of ways. I should have said 3 permute 2, shouldn't I? That's the difference. Oh, no. It's 3 choose 2 times 2 because the other one can either be red or green. That's what I should, so this should have been in that box. And then plus 3 choose 3. So then that would have been 27 minus 7, which is 20. Let's try to do a generating function argument on this. And I'm referring to 338 even though I haven't used it yet. If we take a look at the idea that if x to the k over k factorial is our kernel, then in order to get the same result, basically our sequence gets multiplied by a k factorial to have the same generating function as before. Just kind of keep that in mind. That means that in some ways our sequences are larger here by a matter of k factorial, which we know kind of represents arrangement. So what we'll say here is that to choose a yellow ball, I can either choose 0 of them Or I can choose one of them, and I'm not always going to write x to the 1 over 1 factorial. That's silly, but I will for this one. I have 3 red balls, so I could choose up to 3 red balls. So that'd be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And the green ball, same way, 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. And so if order is important to us, then in our generating function, we put our x's over the corresponding factorials. And that will be the exponential generating function for the sequence where the coefficient of x to the k is the number of ways to arrange k balls from this bag. And if you just kind of glance at it, how many ways can I arrange 9 balls? Well, the only way to get 9 balls is to choose all of them. So that would be x to the 5th over 5 factorial times x cubed over 3 factorial times x to the 1st over 1 factorial. Let's actually do that real quick. So coefficient of x to the 9 over 9, I'm sorry, coefficient of x to the k over k factorial. So x to the 9 over 9 factorial is what we're looking for. In our product, the only way to get x to the 9 is to multiply these terms together. So that's x to the 1 over 1 times x cubed over 6 times x to the 5th over 5 factorial is 120, right? So this would be x to the 9 over 720, or x to the 9 over 6 factorial. So the coefficient of x to the 9 over 9 factorial, I actually have to rewrite this. This would be equal to 9 times 8 times 7 times x to the 9 over 9 factorial. And so that is the number of ways to arrange 9 balls from this set. And we can double check, what about x cubed? Actually, let's go ahead and multiply this guy out real quick. Real quick as a stretch. Let's multiply out, let's do the x cubed one, because that one we had a little trouble with here a second ago. Well, I did, you guys didn't. So how can I get x cubed? I get 1 times x squared over 2. I get 1 times x times x. I get 1 times x times 1 times, hold on, 1 times 1. That's all of them with the 1 there, right? Trying to get, wait a second, did I say I was trying to get x cubed? 1 times x cubed over 3 factorial. 1 times x times x squared over 2. 1 times x squared over 2 times x. One times x cubed over 3 factorial times 1. All right, now x times 1 times x squared over 2. I'm just going to have to start writing them, even though I know we're going to gather them in a minute. That was x times 1 times x squared over 2, x times x times x. That's just an x cubed. x times x squared over 2 times 1. That should be all of them, right? So, hold on. They should all be cubed. What happened is, as I was doing it, I forgot to, let me just redo it here just to be safe. As I was multiplying it, I was forgetting, like if I said 1 times x squared over 2, I just wrote the x squared over 2. So 1 times x cubed. I'm going x cubed over 3 factorial. I'm going in lexicographical order. So 1 times x squared over 2 will be x cubed over 2. 1 times x squared over 2 factorial times x will be another x squared, x cubed over 2. And then let's see. And then 1 times x cubed over 3 factorial times 1. So that'd be x cubed over 3 factorial. There's another one of those. Now, if I start with this one as an x, then times 1 times x squared over 2, that'll be x cubed over 2. And then x times x times x is just an x cubed. And then x times 1, wait, I already did the 1 there. X times x squared times 1 will be another x cubed over 2. And yeah, that's the same as this, except these should all say cubed. So that should be right. So let's see. That's 2x cubed over 3 factorial plus 4x cubed over 2 plus x cubed, which is we're going to want all of these over 3 factorial, so that's 2x cubed over 3 factorial plus 12x cubed over 3 factorial plus 6x cubed over 3 factorial. And so 18, that is 20x cubed over 3 factorial, which is the answer we got before. Of course, we did our multiplication by hand, and that's silly. Once you know what your generating function looks like, you should totally be punching that sucker into Wolfram Alpha to get your coefficients and not doing them by hand like we just did. So then that brings us to theorem 338. If you have a set containing p kinds of objects with ni indistinguishable objects of each type, then the number of distinguishable ways of arranging them, k of them, is the coefficient of x to the k over k factorial in your exponential generating function, which you get as the product of those sorts of polynomials. That was why I wanted to do the example first, is because it's way easier to understand how the theorem works if you've done it with a small example. So then example 340 asks the same question, except the supply of the objects is infinite or we are drawing with replacement. So if we're drawing with replacement or the supply is infinite, then our h of x, our generating function, will look like what? Well, it would be 1 plus x squared over 2 factorial plus so on. And it would just be that to the p, which is, by the way, just e to the px. And so we'd be looking for the coefficient of x to the k over k factorial in that guy. Find ak explicitly by using exponential generating functions. Well, that's equal to e to the px. We have another way of writing e to the px. We can write e to the px as the sum, as k goes from 0 to infinity, of px to the k over k factorial, which means that this is the sum, as k goes from 0 to infinity, of p to the k, x to the k over k factorial. And so the coefficient of this guy is p to the k. Now, that's what we've always had, but that is what we've always had, right? If you are arranging p items from a k set with replacement, that's p to the k. That was like day one, I think. So it's nice that the exponential generating functions give us back some of what we had before. What about example 341? What if we want at least one of each? Well, then that's no empties, right? So we have h of x equals, we can't choose 0 if anything, so that's x plus x squared over 2 plus x cubed over 3 factorial, and so on, all of that to the p. Well, this is equal to e to the x minus 1 to the p, which is e to the px minus e to the p. Not minus. Don't like pull that kind of stuff, right? That's e to, I meant to say e to the px minus p, which is e to the px over e to the p. So this is equal to e to the minus p, say that, times the sum as k goes from 0 to infinity of p to the k, x to the k over k factorial, just using what we had a moment ago. And so this tells me that little hk here is equal to p to the k over e to the p. Give me just a second. I need to grab a water bottle. So at the bottom of page 30, what we've got there is our convolution sum. And the important thing there is that AK convolved, I'm going to call this, put a little e subscript on there for the exponential. Oh, you're right. Man, give a guy a weekend. So Alex says h of x should be e to the x minus 1 to the p, which does look better, this step here. let's see. Now, I think I need to use the binomial formula in order to get my generating function. So this is equal to the sum as k goes from 0 to infinity of -1 to the k Is that right? Hang on. We'll do it the nice way. P choose K e to the x to the k times -1 to the p minus k. Just binomial formula there. And then this guy can be rewritten as the sum as k goes from 0 to infinity of p choose k minus 1 to the p minus k. And then that's the sum as, say, j goes from 0 to k. I can actually stop this guy here. Not, sorry, j goes from 0 to infinity. E is, this will be x k to the j over j factorial. That looks a little ugly. Hang on, let's make that nicer. Let us bring the j sum to the outside. The sum as j goes from 0 to infinity. And then that's the sum as k goes from 0 to p. P was an integer here, so we can't go all the way to infinity anyway. So then we get -1 to the p minus k, p choose k, k to the j, and then x to the j over j factorial. I have done something horribly wrong here. I mean, not horribly wrong. This is bothering me, this k to the j. I think maybe I was supposed to do something else first. Oh, I just switched it. I took this to be my p minus k, and that's, I think, where things are going wrong here. Give me a second. Let me start over at that step and flip this the other way. And so this should be the sum as k goes from 0 to p of p choose k, and then if I put the -1 to the k, and then the e to the k minus, p minus k, p minus kx. It's very similar to what I did here, but it comes out nicer. You don't, you'll see here in a second. So this is the sum as k goes from 0 to p choose k -1 to the k. Now that's the sum as, I used j a second ago. J goes from 0 to infinity of p minus k to the j, x to the j over j factorial. And so then if I swap that out, I get the sum as j goes from 0 to infinity of the sum as k goes from 0 to p -1 to the k, p choose k, p minus k to the j, and then that times x to the j over j factorial. And I know that doesn't look much better than what I had up there, except when you realize that this is almost Stirling's number, Stirling's formula for the Stirling numbers of the first kind. This here is equal to, underline, is equal to k factorial times s of p comma, k comma p. The Stirling number of the first kind. And this, back from theorem 210, something else in the notes, something else in the book, I forget exactly what it was, but the 8-part theorem was the number of ways to permute k items from a set of p with replacement and no empties. And that is kind of the punchline. And it also explains finally where we got that formula for the Stirling number of the first kind. So that was the point of that. I'm not sure why I have it twice in there though. Because that is 341, example 341 and example 345. I mean, I didn't quite finish it there for 345, but it's really, really close. Anyway, that seems like an okay place to end. Also, I've lost my pen cap. That last one was messy. I will probably just go ahead and redo that one. Yes, our sequence is k factorial, Stirling number of k comma p. That's what we were looking for. And I will redo that at the beginning of next class, because I know that when I have a couple of false starts, it doesn't make nearly as much sense. So I'll do a clean version at the beginning of next time. All right, I'm going to stop recording now.